Hi everyone. So in this talk, I'll be talking about the circumgalactic medium of our nearest neighbor, that is large Magellanic cloud. So shown here is the schematic. Okay, shown here is this schematic of our local interacting group, where LMC is one of the important key element of our local interacting group. And given its proximity to us, um, um, given its proximity to us, LMC is a really unique laboratory to study the galaxy evolution closely, mainly in the dense environment. So the important question here is to ask, does LMC has its own CGM? This will be really important because the CGM of the LMC will act as a protecting shield around the LMC gas, and which will be acting as a protecting shield for the gas during its LMC infall orbiting around the Milky Way, and hence it will influence the gas regulation of both not only the LMC but also the Milky Way. So recent development in the LMC has actually found that the halo mass of the LMC is more than 10 to the power 11 solar mass, which is like massive irregular galaxy. So a galaxy of typically this much solar halo mass should be able to hold its own CGM. And the observational evidence of the warm hot phase of the LMC CGM, also known as corona of the LMC, has indeed been found recently by Krishna Rao 2022. What they have found is a declining radial profile for the collationally ionized gas asterisk by C4, Si4, and O6, and as a distance from the LMC increases, which is a characteristic signature for the CGM of a galaxy. The authors found a temperature of 10 to the power 5 Kelvin for this warm hot phase volume filling CGM. They also found evidence for the 10 to the power 4 Kelvin cool gas. So in this study, we studied this cool phase of 10 to the power 4 Kelvin in detail, and also we provide its connection, compare it with the warm hot phase to give a complete picture of LMC CGM. And also in this study, we characterize the spatial extent of this LMC CGM. To do that, what we did, we revisited the sample of 28 quasar sightline of Krishna Rao 2022. And shown here is the location of these 28 quasar sightline in the galactic coordinate. They are color-coded with the distance from the projected distance from the LMC. From this, it can be seen that most of our quasar sightline they are probing the South Galactic Pole and far up to a distance of 35 kpc. Then what we did, we identified the absorption associated with the LMC. So we look for the 15 transition of 7 of the low 10 to the power, roughly 10 to the power 4 Kelvin gas, which are marked here. I'm really bad in this. Yeah, this. And we only look for absorption far beyond 150 kilometer per second in the VLSR space to avoid the contamination from the Milky Way. And then we simultaneously fit these absorption profile. After identifying this absorption profile in 28 quasar sightline, we fit them using VP fit, and we estimated the column density and the velocity centroid of each component of the absorber in 28 quasar sightline. Shown here is the fit of our VP fit for one of a quasar sightline RBS 563 at 8 impact parameter. Now that we know the column density and centroid velocity of these cool gas, what we did, we plotted the distribution of the column density, total column density of the low ion gas as a function of impact parameter. We also combined the data for the Si4 and C4 from the Krishna Rao 2022 study. And then we fitted this column density profile using censored power law model. And this model takes into account the low limit and the upper limit from the saturation and non-detection. So from this plot, following points can be noticed. One, the low ions have a declining radial profile of consistent slope, and high ions also have declining radial profile of consistent slope. So which indicates that LMC does have its CGM and which is also multi-phase. And the second point to note here is the cool gas, the low ion gas drops more steeply compared to the high ion gas, which indicates that the LMC CGM is more ionized at larger distances. Next, we explore the kinematics of this diffuse gas around the Magellanic gas around the LMC. To do that, we plot here the velocity centroid distribution as a function of impact parameter. We are only showing for the 4 ions, but our results are consistent for all the other ions. So we only choose these 4 ions because they represent gas of different phase. So what we find here, this is a velocity distribution, velocity centroid as a function of impact parameter. I'm so sorry, I'm really bad in this. So what we find here is for all these phases, closer to the LMC, the number of components are more compared to the region far away from the LMC. So from this inner CGM, inner region of the LMC is more complex compared to the outer region. And next, we wanted to explore how this gas is distributed around the kinematics velocity of the LMC, which is 280 km per second, shown in the horizontal black line, dashed black line. We also plot the plus minus 50 km around this velocity. And to do that, what we do, we estimated the column density weighted centroid velocity around each sight line, and which we show here with the dark blue star points. So from this plot, interestingly, we find that most of the LMC, the absorbers which are mostly associated with LMC, they are found only up to 17 kpc distance from the LMC. The magenta vertical band marks this velocity jump in the impact parameter space, which is roughly close to 17 to 20 kpc. And we find that mostly the absorbers beyond 17 kpc, they are mostly found at a lower velocity. So we conclude here that the LMC CGM is comprised of 2 elements. One is the non-tidal inner halo, and the second one is the extended strip region, which is associated with the stream. So from this, we conclude that the LMC CGM, the non-tidal inner region, is extremely compact, which is 10% of its virial radii. And to further probe this, how it correlates in velocity with the H1 neutral H1, how this ionized gas correlates with the H1 neutral gas, we plot here we compare this UV velocity with the H1 emission velocity. To do that, in background, we show the H1 emission velocity map from the Westmeyer, and for the sight line with less than 17 kpc, we show them UV sight line less than 17 kpc, we show them with circle, and for the sight line beyond 17 kpc, we show them in stars. So as can be seen from here, that the velocity of the UV gas beyond 17 kpc is pretty much consistent with the H1 emission strip gas from the stream. So and the this indicates that the outer CGM is actually ramp pressure stripped and decelerated to the lower velocity, consistent with the stream velocity. However, the non-tidal inner halo is truncated up to 17 kpc. And this truncation length scale of 17 kpc is actually consistent with the simulation prediction based on the ramp pressure stripping of the recent study by Lucchini and Zhu. And next, we argue that this truncation is due to, because LMC is not isolated, it is constantly interacting with the Milky Way and the SMC. So we argue that this truncation of the LMC LMC inner halo is due to the environment effect. So to do that, what we do, we compare our LMC profile with the isolated dwarf galaxy sample given recently by Zheng et al. So when we plot their profile for these ions, we find that LMC profile is steeply and abruptly declining compared to the isolated galaxy. If at all, LMC is more massive compared to this dwarf galaxy sample, which is roughly 10 to the power 8 solar mass. So this is showing the strong indication for the environment effect occurring towards the truncation of the LMC CGM. And while it is interesting that, but majority of our sight line, as you have also notice that they mostly probe towards the south galactic pole. And literally there is no other sight line in this region, mainly because this lower latitude region is, because of the galactic disk extension, you don't have enough UV bright quasar. So until recently, the plain quasar sample by JS was out. So we used this catalog, planar quasar sample catalog, and cross-collate this to identify the sight lines, UV bright sight line around the front side of the LMC. And we indeed find 5 sight lines probing the front region of the LMC. And this region is particularly important because this is directly exposed to the interaction with the Milky Way. So various other processes like bow shock and all can be directly probed using this, these sight lines. So we have luckily got 29 orbit to observe these 5 quasar sight lines. So stay tuned for the more results from the front side of the LMC. And this is my summary.
Questions?
So, Sapna, you showed the number of components as it dropped with distance. So, do you have an interpretation for it? Is it something just the path length is more, or is there some kind of a clump gas distribution that can produce the component structures?
Yeah, there is one thing could be because the inner region is more dense, and we in our paper say that this gas is like this cool gas is the cool and the warm phase exist in the interfaces, and since the inner region is more dense, so there you have more cold gas, so more interfaces are there, and as you are moving away and away from these interfaces are decreasing because the gas density is decreasing there. So
something like an NFW profile?
Yes, yes.
Thanks.
Yes?
If you could go back to the profiles, a couple
Okay.
slides. Or sorry, like second to last slide. This one.
Yep.
Yeah. I see the truncation, and I was also wondering, because I've seen some papers recently that talked about how ram pressure not only strip outer gas, but drive inner gas more inward through loss of angular momentum. If you're seeing higher concentrations of gas towards the center, that you would attribute to stripping as well.
Oh, that's interesting, but I have not explored that.
Yeah, it depends on the
Yeah.
angle of interaction
Yeah,
with the
yeah.
wind, but the angular momentum loss at a certain angle can cause gas to fall inward.
Yeah, that's
It'd be
right.
cool if that's also used.
Yeah, that's interesting. I'll explore that. Yeah.
Other questions? If not, let's thank the speaker.